Good morning and happy March 26th. Today is Thursday. So, two things before we get started here. First, you will have a quiz tomorrow. Same format as last week, and this will cover the entire energy unit. All right. You should probably concentrate on kinetic and potential energies and the law of conservation of energy. All right. However, today, as is my custom, I'm going to start with the next unit, which is, as you can see on the screen now, the unit on electricity. This is a huge jump. All right, we're moving away from mechanics and classical physics into the second of three major topics. Now, this won't take 6 months like mechanics and statics and dynamics did, but it's a very important unit, one that has a lot of very practical applications. In any event, when we talk about electricity, we always begin, or we should begin, with what we call static electricity. Now, static electricity deals with electric charges that are essentially stationary. That's where the term static actually comes from. But more importantly, this deals with electrical charges that can be gathered, collected, and held in one place, like, for example, a battery or in your finger, all right? And when are those released? Well, when you go and touch a doorknob or your car door or something along those lines, you get a shock, right? That is the release of those electric charges that have been collected and held in one place. Now, a fascinating little story goes on with Benjamin Franklin. Believe it or not only was this man one of the founding fathers of the United States, but he was also a scientist. Now, most of you probably know that from Mr. Hayes' class, but it's something that we don't often talk about. When you say Ben Franklin, you say, oh yeah, he was one of the founding fathers. But in reality, he did a great deal of work on what we today know as static electricity. He actually coined the terms electricity and the words positive and negative as regarding these electric shocks. He did his work studying lightning. And although the story about him flying the kite with the key and all that nonsense is probably apocryphal, because if it was absolutely true, he probably would not have survived the encounter. He did work with lightning and created what is today known as a lightning rod, tall metal post that sits on the top of a house or a barn or somewhere else high up in elevation. And Franklin theorized that lightning was actually the result of the recombination of the positive and negative charges. And we'll talk about that some more a little bit later on. Now, in terms of static electricity, there's a couple of things that I want you to be aware of. First, where do these electric charges come from? Well, as you learned in Mr. Leonard's class last year, the electric charges that we are talking about really emanate from the electrons, the negatively charged electrons that you find in an atom, and the positively charged protons that you find in the nucleus of an atom. And this discovery really came about with a guy by the name of Joe Rutherford and his gold foil experiment. And in this experiment, he demonstrated that atoms have a positively charged nucleus. We now know that that's because of the protons located inside the nucleus, and negatively charged electrons that are in orbit around the nucleus. All right, and Joe Rutherford did his experiment and was able to demonstrate essentially the structure of an atom. But it was important because he also illustrated that the positives and the negatives were not found in the same place. The charge on an electron, and by the way on a proton, was discovered by Joe Thomson. And each electron has what we call a charge of 1.60 times 10 to the negative 19th coulombs. Coulombs is a unit of charge equivalent to the collection of 6.25 times 10 to the 18th electrons. Now, the 1.60 times 10 to the negative 19th coulombs is considered to be one elementary charge. And if you look on the front page of your reference tables, you'll find a lowercase q. Q equals 1.60 times 10 to the negative 19th coulombs. If it's a positive charge, it's an electron. If it's a I'm sorry, let me start that again. If it's a positive charge, it's the charge on a proton. If it's a negative charge, it's a charge on an electron. Okay, but 1 coulomb has a charge, or is 6.25 times 10 to the 18th electrons all put together. Now, on the next slide, this is a link to a video that I found on YouTube regarding Rutherford's experiment. And I don't believe that you're going to be able to click on that link while you're watching this MP4 play. So I'm going to attach both this video and the PowerPoint that you're seeing behind, so that you can click on this link and go to that video. It's just an interesting little video and something new and different. I was getting bored with the videos that I'm making, and quite frankly, I hate staring at myself in the upper left-hand corner of my screen. So, so go back to, open up that PowerPoint, and look at that video as well. Now, static electricity. Why do we have static electricity between, our finger and the doorknob and that sort of thing? Well, it is possible to transfer electrons from one atom to another. Okay, and you know that because that's the basis of all chemical bonds, even especially ionic bonds. But if you do work on an atom, you have the potential ability to remove electrons from that atom and create a positively charged ion. If you add electrons to an atom, you create a negatively charged ion. And you experience this all the time. If you walk across a carpet, for example, in your socks, all right, you will build up a great static charge in your body. And then when you go and touch a metal door handle or some other metal object that's grounded, those electrons will be able to either escape from you into that object or escape from the object back into you, depending upon your net charge. Examples of this that I would love to be able to demonstrate to you, and if we were in our classroom, I would be able to. But glass and silk, if you take a glass rod and a silk cloth and you rub them together a little bit, the electrons will move from the glass to the silk, and the glass rod will become positively charged. If you rub a rubber rod and rabbit fur or squirrel fur, the electrons will do the same thing, except this time they move from the fur to the rubber, and so therefore the rubber rod becomes negatively charged. Right? I will demonstrate this to you. I'm praying next week if we go back to school, but we'll see how it happens. But at some point I'll show you how this works. Now, there are three kinds of materials that you need to be aware of in terms of static electricity and even current electricity, which we'll get to later in this unit. But they are conductors, insulators, and semiconductors. A conductor is simply a material through which electrons will move. And the best example of conductors that we have are metals, right? The wires that run from house to house and transmission line to transmission line are all composed of metal. Mostly aluminum. So, within your house, they're probably made of copper, unless you have a very old house, in which case they may still be made of aluminum. Insulators are materials through which electrons will not move. Things like this include rubber, glass, plastic, wood, dry air. Right? Electrons will move through wet air. That's what lightning is. Or even pure water. Pure water will not conduct electricity. But again, one of the reasons why we cover our wires, the wire to your computer or the wire to a lamp, we cover it with rubber or plastic to prevent the electrons from escaping from the conductor out into the environment. The third and final thing on this list is what we call a semiconductor. And these are materials which resist the movement of electrons but permit it. Okay, we will talk about semiconductors in great detail after we finish the unit on electricity, because they're very important in electronic uh, machines like cell phones and laptops and that sort of thing. All right, but again, we'll revisit that at some other point. As I'm sure that you are already aware, there are multiple ways that we can look at two charges. Okay, if you have two charges and one is negative and the other is negative, those two charges will repel one another. Like charges repel each other. All right, so the electrons repel each other. If you have a negative charge and a positive charge, they will attract each other. They will be drawn toward one another. And finally, if you have two positive charges, they will repel each other as well. Now, think about this. Mr. Leonard probably just told you that, oh yeah, all the protons in an atom just kind of hang out together in the nucleus. Well, think about that. If all those positively charged protons are sitting in the nucleus, all right, they're trying to repel each other. So there's got to be a great deal of force holding those protons together. That is the strong nuclear force, which is why we can get so much energy out of nuclear reactions. In any event, again, that's something we'll visit again later on in the year. Okay. Now, so again, there are two kinds of charge, positive and negative. These charges exert forces. So we're still going back to the statics and dynamics stuff. F equals ma and all that nonsense. So charges exert forces on other charges over a distance. And this will become important for our next lesson. And finally, like charges repel, and of course, opposites attract. All right, my friends, that is the end of today's lesson. Again, please go back and open up the PowerPoint here so that you can click on the hyperlink to the YouTube video on Rutherford's experiment. There is no homework for tonight except to study for tomorrow's quiz. All right, again, concentrate on kinetic and potential energy, because that's where we'll be focusing here. All right, have a great day, and I will talk to you tomorrow.